really bright.
Sorry? Yes, it's super intense, no? Like,
Yeah, so Edwin,
Edwin.
yeah,
Yes. Ah, you are the next one, right?
yes, I am.
Okay, that's great. Yeah, because I was thinking like, what is the next person? Ah, you are lovely.
Yeah.
Right. Where did you go, Customers?
Yes, I was. I didn't see you there. I don't know, for some
That's
reason.
weird. Like I was there, and I'm thinking, sounds like
Yeah,
I don't recall seeing you. Well,
yeah,
well, good to meet you in
yeah.
Vancouver instead of.
Instead of customers, yeah. I've been there. Yeah.
Cool. How did you enjoy Cosmos?
It was good. I really enjoyed it. There was quite a wide range of different
Yeah.
topics this year. I think I was there last year as well,
Mhm,
and it was much more focused on machine learning,
mhm.
on P4 and hardware programmable devices,
Yeah.
whereas this year was a bit more.
It depends a lot on the year. Like, I mean, there are always more demands for presentations than slots available. Same with people. Usually, there is quite a few people that cannot make it because we simply don't have room. Hey, Leslie. Okay. There was nothing terrible, but yeah, no, fair enough. Thank you. That's good because
Yeah, we're not seeing bad things.
we are not seeing buffing. Buffing. I like this transcription. Can we play with the transcription? No, I didn't say buffer. I say buffing. All right, welcome back, everybody. Oops, there is some echo. Ah, okay, sorted. So the next session is about security and energy, and the first presentation is about low carb BGP, a carbon aware interdomain routing extension to BGP, and it will be presented by Edwin Sutherland from Loughborough University. Edwin, the room is yours.
Thank you. Hi, everyone. I'm here to present low carb BGP together with Ian Phillips. We have been doing this research just under a year since we participated in the Carbon Aware Networks workshop in Oxford University last year. So to talk about the motivation, why we interested in sustainability on the internet in the first place? Well, depending on where you read this information, there's some reports up to 3 to 4% of the global CO2 emissions is contributed by the ICT industry. And if you break that down a little bit more, you see that there's three main elements that factors into this. Data center infrastructure, which we all know with the rise of AI workloads, is ever more expanded. But there's also end user computing devices and networks. And all of these are contributing to the CO2 emissions that as a planet we need to be aware of and to try and to reduce. Um, Another important metric to be aware of is that there's also the growing trend of the internet in terms of generating traffic. So we have a predicted 60% global data growth over year on year moving forward. So there's an incumbency on us as network operators, developers, to think about how we can make the networks more sustainable moving forward. So the key idea I want to present to you today is that to make the internet and networks greener, effectively, we need to make ISPs want to be greener. And to do that, we create an incentive or a motivation where ISPs will decide to route traffic and prioritize traffic over greener ASs as opposed to just choosing the shortest path first. And by incorporating greenness into routing policies, we believe that there's a mechanism where ISPs will be more profitable in terms of those receiving more traffic, and potentially change the dynamics of the internet where we are creating a race to the bottom where everyone wants to be greener. That's the ideal world. Maybe it's a fantasy, but let's see how we can move towards that direction. Okay, so how do we measure greenness in the first place? There's some ideas that have been proposed by the IETF. Some of these are, for example, taking into consideration the carbon intensity. Carbon intensity is the CO2 grams per kilowatt hour of electricity used. And in this case, we can effectively measure the effectiveness, the carbon efficiency of networks using this type of data source. Also, in a way, it's a bit more, I would say, equal in terms of whether you're a big operator or you're a small operator. It doesn't really matter, because what we're trying to focus on is how efficient you are in terms of your carbon emissions. Another way you could measure this is through something like a carbon performance rating. If you're familiar to how houses are often rated for their energy efficiency, we can implement some kind of rating system around how different network operators perform from a carbon footprint perspective. In either case, we envisage that there will be an external auditor that will carry out this work to hold networks accountable for the submission or the publishing of their carbon intensity or other green metrics that we might want to use in the future. So fundamentally, what we want to be able to do is to identify that an AS that is using renewable energy is more carbon efficient. Therefore, we want to route our traffic through those ASs. And the ASs that are using more pollutant energy, we want to discourage them from using pollutant energy. Therefore, one of the ways to do that is not to send our traffic through them. And by doing that, they may have a motivation to say, well, actually, we want to restrict traffic, so let's carry out some energy efficiency or carbon efficiency exercises or programs in our infrastructure to appeal to anyone that wants to be on the path for making greener decisions. So we built a system called low carb BGP, and essentially low carb BGP is an SDN controller that will sit within an ISP's network. It will retrieve the green metric from some kind of central database. It could be an RPKI system. It could be something else dedicated for greenness. And it will distribute the green metrics that belongs to that ISPs through their autonomous border routers. So this information will get disseminated throughout the internet, so everyone will be aware of the carbon intensity value for each AS. The other function of low carb BGP is to retrieve prefixes that have been advertised to that AS and to work out what the carbon intensity for each path that is received for different prefixes. And we'll go into this in a little bit more detail. We can then aggregate that information in some fashion that we can then use to make routing policy decisions on. Once we understand that, we can formulate those routing policy decisions and push that down to the network devices to make the decision. So the dissemination, what we played around with this so far is to use extended communities. And although this might be malleable in some sense, there could be other ways to provide attestation. For example, maybe not using extended communities, but using RPKI as an example. But in our test environment, we're essentially using an extended community to encode the carbon intensity metric in this case. We do this in an additive fashion. So if everyone plays nicely, we get what we call a SIM chain, which is effectively a breadcrumb of the carbon footprint of routing to a specific prefix. Once you have that information, you can then start maybe potentially doing reporting on that to understand your carbon footprint in terms of your contribution overall in the internet. We can then aggregate that information. We can, for example, have what we call the total carbon intensity metric per prefix, and we can make routing decisions based on that information. We can calculate the median of the carbon intensity from that chain, or maybe we want to be more picky and say we want to avoid certain carbon intensity values. So the highest carbon intensity value within a chain, we want to avoid that path and select a different path. And then lastly, you could do some more data aggregation if it makes sense to reflect that. And this could be, for example, the median TSIM on a per neighbor basis. For policy formulation, there are different ones. The ones that we tested in our environment was the greenest path first. So in this case, I'm interested in only routing, picking a path with the lowest total carbon intensity metric. You could do things like having a budget for the carbon footprint of a path or a prefix, and then you can decide that beyond that budget, you want to deprioritize that path, as an example. Other things that could be considered is multi-objective optimization, where you're taking greenness as part of the equation in addition to the administrative and performance requirements of a provider. So in our test bed, what we've set up is essentially use electricity maps. There's a platform out there that reports on the carbon intensity on a geographic basis. And we use the Catharos emulation platform to emulate the Geant topology, which fits nicely because most of the ASs within the Geant topology are geographic based. So that was quite an easy test bed to put together for the purpose of testing. What we've done is to try and figure out, well, can we calculate some of these metrics on a per previous basis? And what does changing the routing policies to greenest path implies? What are the results compared to classic BGP? So to do this testing, essentially from each AS in our topology, which was around 38 ASs, we check in every single destination prefix and checking their path and calculating their total TSIM values. So the results that we gained from this, when we did the comparisons on the x-axis, you see all the different ASs in our topology, and on the y-axis is the median score. So on your left-hand side, on your right-hand side, sorry, is the median total carbon intensity metric, and that represents for any particular AS on the x-axis all possible destinations that they could get to. What is the median TSIM for that? So as we can see in the graph there, there isn't a dramatic change, although in most cases, low-carb BGP performs better from a carbon efficiency, from a carbon footprint perspective. And as the graph shows, there's some instances where there's a significant savings from a carbon footprint perspective. On the right-hand side, on the hop count side, you see the comparison between low-carb BGP and classic BGP from a hop count perspective. So has there anything changed from a hop count perspective? And the intuition that we got from this is actually the greenest path is most often the shortest path because of the cumulative nature of the TSIM aggregated metric. So again, it shows you here that although we introduce greenness into the equation, we're not making a drastic change to the way that the topology routing perspective is done and the outcome of the results. So we'll look at two cases. So in this case, this is the best case example where low-carb BGP shows significant improvement in terms of lowering carbon footprint. So in this case, we have from AS 5538 to AS 13092. And in this case, we're going from top to bottom. With classic BGP, there are fewer hops, but what we've traded for 2 extra hops is the reduction of the carbon footprint by up to 67%. So in this case, you could say that's a good trade-off, depending on the context and whether latency is affected in a significant way. The worst case example here we see from AS 2614 to AS 5538. In this case here, although we're going to the same destination, low-carb BGP decided to avoid certain ASs because of their significant carbon footprint and decided to trade off 5 extra hops just to gain 37% reduction in carbon footprint. So as you can see here, this is not exactly a nice outcome. And depending on practicality, this is definitely not something that some operators will be happy with. And therefore, one of the things we want to look at in the future is the multi-objective scenario where we can actually enhance local BGP to be more considerate. An interesting analysis we did here was, well, what happens when local BGP gets put into effect, where there are, depending on the topology, where there are ASs that are more central or more transited to. What is the change here? And what we see is actually, I think, is quite significant and could be a motivator. So in the top 5 lists, there's no change in ASs from classic BGP to local BGP. The top ASs remain more or less the same. And this is most likely due to the centrality of those AS within the topology, but also their carbon intensity value as well is advantageous in this case. But when we look at the bottom 5, there's been a dramatic change because there's the ASs that were in classic BGP that were often transited through are no longer there in local BGP, because local BGP favors transiting through ASs with lower carbon intensity values. We see that this has significantly changed. So if you are in AS 57961, you're no longer receiving traffic, which might be a motivator to reduce the carbon footprint. So overall, what we found in our testing was that local BGP actually reduced overall carbon footprint routing between the different ASs within our topology to reduce the carbon footprint by around 20%. Now, this might not be significant in terms of the percentage-wise, but we believe that every little helps and improves the emissions rate of operating the internet. So conclusions, what we've learned from this work is that local BGP has a nice property of overlapping green economy with internet routing. And if we have the right incentives in place, we can motivate ISPs to start making greener routing decisions, which obviously from an internet perspective has a compounding effect in helping to move this forward. Local BGP is also adaptable to the current interdomain routing paradigm because we don't make any changes to the BGP algorithm itself. All we ask for BGP is to advertise community values. There's an SDN controller that has context of that information and is able to manipulate BGP using the existing best path selection algorithm. What we want to do moving forward is to experiment with different inter-AS level topologies, try different green metric types. Maybe instead of having a single green metric, we can have multiple metrics that we can evaluate against, and also do some work on the multi-objective optimization. So that's all I wanted to present around local BGP. Open for questions and suggestions moving forward.
Thank you very much. We have time for 2 or 3 questions, depending how fast they are. Sharad, you're next.
Thank you very much. This is a really interesting piece of work, and got my intellectual juices going. So thank you. Here's my question. Let me try and phrase it, which is, I tend to think of peering geographically. So, for example, let's say I want to peer with a customer or an ISP. I will need to think about what is the catchment area that I want to try and get, and okay, maybe I need to peer with them up here in Vancouver, or maybe I need to peer with them in the southern US. And so my question is the following: when I'm sending traffic, right? What I'm often choosing between is which of my peers, here in the Pacific Northwest would I send traffic to? And up here, the majority of energy tends to be green, we've got lots of, water-based energy that we have here, versus like maybe in the southern US where maybe there's more dinosaur burning that's happening. So what I'm wondering is like, in your analysis, like where does the majority of difference come from when you're sending traffic between a choice of different peers in a particular location? Like where does the source of difference in their carbon footprint come from in a particular geographic location? Because yeah, I guess greenery depends on where you are.
Yes, there's a couple of things we want to dive into in relation to that. So obviously, we're always aware that the internet is becoming more one hop away from anything, right? So
Yep.
the density there. So what we want to figure out is the carbon intensity value to actually represent the ingress and egress pairing of traffic going through an AS. And that way we can be more granular around the selection of which peer to send traffic through. But ultimately, we don't really care about the neighbor, we care about the path. So we want to go for greener paths rather than I'm going to pick this neighbor because it's green, because your nearest neighbor might be green, but downstream from them, they may be using more pollutant ASs, and we want to avoid that.
Okay. All right. Thanks.
I'm sorry that the queue is closed. I know other people want to make questions, but I would really appreciate if people can make questions relatively fast and the answers can be relatively fast because we have already run out of time. Please, Jonathan, I think you are the next one.
Yeah, Jonathan Hoyland, Cloudflare. So if you give an AS a score saying, oh, this is very green, and another one a score saying this is not very green, is there a risk that people will be like, oh, I'm going to send all my traffic through the green AS, which is going to make it really congested, which is going to mean there's lots of retransmissions, which means there's going to be much less green?
I think the green AS will be happy to retrieve more traffic if it impacts their revenue, right? So they will find ways to accept more traffic. But in saying that, yes, there could be polarization in doing it this way.
You'd end up with much less green.
I'm sure there's a debate there to be had, which will continue offline. Matt, you're next.
Yes, I have a sort of a different question along the same vein, and that is for a lot of technologies, the base power dissipation of a routing device or whatever is independent of the load on it, and the incremental energy depending on the load is different. And it matters a whole lot how you average that base capacity out, and particularly a heavily loaded router looks more efficient. How do you calculate those numbers, and how do you justify them or audit them?
That's a really great question. I think with the carbon intensity metric, we are looking at the source of the energy rather than the utilization of the energy, right? So you're more carbon efficient if you're using sustainable energy, like one professor told me. If all you're using is solar, you can use as much energy as you want because you're still being carbon efficient. So we want to look at the carbon efficiency rather than the energy efficiency. Now, the energy efficiency could influence that, but the carbon efficiency is much more important.
So for instance, in networking technology, deep buffers are extremely expensive in terms of power, and they have vastly different capabilities in terms of performance.
Thank you very much. Let's thank the speaker. And let's welcome the next speaker, Justin Uhrman, talking about implementing and evaluating UAM integrity protection. The room is yours.
Yeah, it's complicated, right? Hi, everyone. So, as the chair mentioned, I'm going to talk a little bit about integrity protection of IOM. So this is a work related to a draft we have here in the IETF in the IPPM working group. So we just went out of this group, and so the draft is progressing well, sorry. So yeah, let's just have a look at the journey we went through for this work. So a bit of background on IOM for those who don't know that. So basically, you want to collect telemetry data on your network. So what you do is that each hop on the path would just insert telemetry data in the packet itself. So you don't need, synthetical traffic for that. In this case, this is just an example of IOM with the IPv6 data plane, but you have some other encapsulation protocols defined for IOM. And so on the edge of your domain, even though the IETF doesn't have, a definition or consensus on limited domains. But anyway, let's call the first node the encapsulating node. So it would just, pre-allocate some space in the packet for the data. It would add its IOM data and then forward the packet. And so you got some transit nodes on the path that would add, if they are configured to do so, they would add the IOM data. And then on the other side of your domain, on the other edge, you got the decapsulating node, which would just, remove the IOM option, so the header and the data. But the thing is, here, the data, so everything that is IOM related is in clear, right? And while you don't necessarily need confidentiality because it runs inside your domain, you probably want to have some integrity protection, right? Because what happens if a node that is compromised would just, modify your IOM data? Well, it could, hide some potential issues in your networks, or the opposite actually makes you think that there is a problem where it's fine. So you really want something to make sure that the data is clean. And so this is why we add integrity protection on IOM. So basically we would just, add an extra header in between the IOM header and the IOM data. And so the encap node would just proceed as usual and initialize that ICV. The same for the transit nodes that would, just update the ICV step by step. So you kind of have a chain of ICVs, just like a proof of, on the path. And then the last node would just validate the ICV. And so the output is either yes, the integrity is intact, so you can just ingest the IOM data, or there is a problem with the integrity, so just ignore this IOM data. This is the extra header that we add. So basically you have a method ID field. This guy is just there to tell a node which method it has, which algorithm it has to use to compute the ICV, basically. You got a nonce that is from a variable length. So you got a nonce length, to specify its length, even though some methods might, force a specific size. But anyway, you want a generic header for every method. And you got the ICV. So this is integrity check value. Right. So I'm going to review a little bit all the possibilities we went through because, there were a lot. And all those options, let's call them options, will use GMAC, which is actually a mode of GCM. And this kind of using GCM with a null encryption. So the only output you have is called an authentication tag, which will be our ICV here. So we are obviously in symmetric keyword. So what we do here is that the encapsulating node would just take the header, only immutable fields, its IOM data, and it would GMAC the whole thing. That would be the ICV value. Then it forwards the packet to transit nodes. A transit node would just check the header first, so it would have to, compute another GMAC to compare. And then if it's fine, re-GMAC the received ICV with its IOM data. So you kind of, form a chain of ICVs, as I mentioned. And so the decap node at the end would have to recheck the whole chain. So it's a little bit heavy, but this is the purpose of this method, which is the validation at the end. And so obviously you get header check on transit nodes with this technique. So this is the version we specified in the previous version of the draft. Right now this is 09, so this was the last one. The advantage is to have header check on transit nodes, but it is really expensive and it was made optional because of that. Why is it expensive? Because you have a chain of ICVs. And so if you want to check the header, you have to recompute the whole chain up to yourself, which is really not what you want, right? And obviously this is not considered a zero trust solution in that case because each transit node would need the key from the encap node in order to check the header, right? And we really want to find a solution that is a zero trust one, right? So let's try just to improve this one. And obviously the idea is to just, add an extra ICV in the packet so that you get an ICV for the header, an ICV for the data. And so each transit node would just, be able to compute the ICV and so check the header as one step. So that's the improvement, but on the other way, you get an extra nonce and an extra ICV. And so it's not that desirable because we got some space constraints, especially in the IPv6 data plane for IOM. Also, you got the encapsulating node that performs 2G max. So while it's not, the end of the world, it's, again, maybe not perfect and not what you want. And since you got check header on the transit nodes, it's, again, you have to share the key from the encap node. So again, it's not a zero trust solution. So we need to think a little bit about this and answer this question. Do we really need the header check on transit nodes, actually? So if you think about it from the perspective of the IOM processing, the answer is yes, maybe it's desirable, but if you take it from the other side and you think about the integrity protection of IOM data, then the answer is no. It's not necessary, right? And actually it's fine because the initial goal we had when implementing this draft was to protect, the IOM data, not necessarily the header, especially on the transit nodes, right? And obviously, if you want a zero trust solution, so if you don't want your nodes to share their keys in between them, you have to use a method that does not implement header check on transit nodes. So let's have a look at how it works. So again, it's called validation at the end, but this time with no header check on transit. So basically the encap node would just GMAC the header and its IOM data fields. And this time the header would be only a selection of immutable fields, but that are really tied to context and provide meaning to IOM data, right? If it's only an immutable field required for the processing, you just don't care about it. So you don't need to include it. A transit node would just, it won't check the header, so it's just one step in this time. So you take the previous ICV you receive and you GMAC it with, the IOM data. Same up to the end, and so the DCAP again would check the header, would check the full chain, sorry. So the advantage is that, as I mentioned, this is a zero trust solution this time. And I guess that we could, have as a cons that there is no more header check on transit nodes, right? But as I mentioned, this is kind of a compromise and an improvement from option 1A and 1B. So we can live with it. In case we cannot live with it, we still got some options. So this one was suggested initially during a sector review from Ben on the mailing list. Let's call this one a neighbor validation. This one is actually easy. So basically what you do is that the encap node would GMAC the whole thing. So here you don't exclude some fields. You just GMAC the whole option, the header and the data fields, and you forward it to the next node. A transit node would just check, the ICV received from the neighbor, and then do the same. It would re-GMAC the whole thing. So it's really a point-to-point, neighbor-to-neighbor validation in this case. So back to the advantage is the header check on transit nodes. But again, we are back in the no zero trust solution. So it's kind of a compromise again. Right, we have IPsec too. So let's call it option 4. The advantage is that you can just, reuse what's already there. So it's provided to you. You don't need to require to redefine a new protocol, right? But it's kind of messy because you would need IPsec channels configured all over the place in between all of your IOM nodes, right? And we're still in a no zero trust solution. But the most important point here is that it may change the path taken by packets. And this is certainly not what you want here, because the goal of IOM is to be, when a packet takes a certain path, if you insert IOM in the packet, you want it to make sure, you want it to take the same path. So that's really important not to have this disadvantage. So it's just, cited here, but probably not that good. Right, let's have a summary of all the options so that I don't get people lost. So the first column is the number of ICV in the header. So if you look at option 1B, this is the only one that has 2 ICVs. So remember, this is the one that we wanted to add an extra ICV in order to make a one-step transit header check on the transit nodes. Then you got the header protected. It's protected. Is it protected? Yes, no, or partially inside parentheses. Do we have header check on transit nodes? Yes, no, or optionally into parentheses. Is it a zero trust solution? Yes or no? And then we got the number of GMAC operations for the NCAP node, for a transit node, and for a DCAP node. And so, as I mentioned, this is really a goal to have a zero trust solution. So if we look at this column, we have only one solution, right? We have only option 2. So of course, it's a little bit heavy on the DCAP node because it has to revalidate the whole chain. And so if you look at the last column for this one, you got n minus 1 Gmax to do, right? But again, this is a compromise because it matches what you want on the other side. So option 2 was kind of an improvement and compromise with 1A and 1B, so you can just forget about those two. But if you look at option 3 and 4, you can see that all values are the same. And specifically, the DCAP node is constant. So there is only one DCAP, there is only one GMAC on the DCAP, sorry. So since they are the same, and from what I mentioned on the previous slide, we will just pick option 3 because it's lighter than using IPsec or option 4. So I will try, we try to implement those two and to evaluate them. So keep in mind the last 3 columns. So if we look at option 2 and 3 for the NCAP, transit, and DCAP, we got basically the same value for the NCAP. So there is only one GMAC. For the transit node, option 2 is 1 GMAC, while option 3 is 2 GMACs. And for the DCAP node, option 2 is n minus 1 GMAC, so you have to validate the whole chain, while option 3 is only 1 GMAC. So obviously, you should see on the graph some equivalence for the NCAP and transit and a difference on the DCAP. Right, so top left, the NCAP node. And yeah, by the way, and the blue line is vanilla IOM, so just IOM without integrity protection, which will be our baseline here. The orange line is option 2, so validation at the end with no header check. And option 3, neighbor validation, is the green one. It's the same for all graphs. So if we look at the NCAP node top left, we can see that they are quite equivalent, right? You see a little bit more drops for option 2, up to a certain percentage of insertion of IOM, but it's quite the same, which is expected, right? Then at the bottom, transit node, we see that after 10% of injection of IOM in the traffic, you got more drops with option 3, which is, if I go back to the slides, is kind of expected because you have 2 GMACs instead of 1, right? But again, it looks like it's not, that much. Now let's have a look at the top right graph, which is the DCAP node. And so here might be surprising because you see that the green and the orange lines are perfectly aligned, or almost. The reason for that is that we wanted to have a common basis for comparison. So in that case, the orange line, so the validation at the end with no header check on transit node, is the case, this is the best case. So this is with only one validation. So you want to know what happens if we had more validations to do, then here we are. So obviously here you see that it fits up to 10 validations if you don't exceed 1% of insertion, right? If you don't exceed 0.1% of insertion, you can just fit the maximum number of validation. And it may seem a bad news from performance perspective, but actually I've discussed with a lot of operators right here. And the average size of domains that they told me is usually 5, maybe 10 nodes. So, you know, it's in that range. But based on this graph, the recommendation is certainly to have either not more than 0.1% of insertion or not exceed 1% for up to 10 nodes to validate. Right, so a quick conclusion on this. So as I mentioned, the draft has a new version, which is 09, and now it specifies the option 2 and the option 1A, if you remember, which was specified in a draft in previous version, was abandoned. We also provide, you know, because it might seem scary, this one, but we provide some mitigation for risk, for performance risk, by allowing the DCAP node to delegate the job of validator, so that you put the validator job out of the forerunning path, and that could be, you know, a good alternative. We still maybe want to have option 3 defined somehow, so we can just, you know, specify it in a separate document later if there is a need from someone. This is actually our plan. Should you want to use option 1B or option 4, well, it's not that worth it. If you need that, then you probably can just use option 3, because they are quite equivalent from an advantage and disadvantage comparison. Although option 4, so IPsec, could be useful for inter-domain use cases. So say you have your domain, domain A, and another remote domain, domain B, and you want your IOM data to transit over that unsecure path. Well, just configure an IPsec tunnel between the two, right? And I guess the conclusion, the real one, is that it was a journey, and it was really a story of compromise. And obviously there is no perfect solution. So we got option 2 and option 3. And depending, you know, on the context and the situation of operators, they might use one or the other. So that's why we want to provide the 2. And that's it for me. So if you have any question, just ask. Thank you.
Thank you very much. Questions? Juan Camilo?
Hello, Justin. Thank you very much, and congratulations, because this work not only was accepted here, but it seems had a reflection in a working work draft. So congratulations. I'm not an expert on the protocol, so I was just wondering, will all situations, in all situations that the protocol defines, is it enough that you have the validation at the end, or does the protocol have any kind of cases in which it doesn't need to look into the packets in a transit node to do some kind of operation?
Yeah, so basically here I use the trace option type as an example, because that's kind of a special beast that is problematic for the integrity protection. So usually the other option types would fit well with even option 2 or 3. So I think the use case for option 2, so the validation at the end, is really if you don't want to trust even your IOM nodes. So you don't want to trust anyone in your domain, even if it's your domain. And if you're not that paranoid, you could go with option 3. In that case, you would trust your IOM nodes, but let's say you got middle boxes or some other boxes in between, those you don't trust. So yeah, it depends on the situation, and I think it's really up to the operators to decide what to use.
Okay, thank you very much. Let's thank the speaker again.
Thank you.
And our next presenter remote is Christina Kada. No, sorry, Shyam Krishna Kada.
Yes.
Who will be presenting Assessing the Security of Internet Flag, a case study of Dutch critical infrastructure. So the room is yours.
Hello, everyone. Can you hear me?
Yes.
Okay, that's great. Welcome to my presentation. I am Sam Krishna Khadka, a PhD student at the University of Twente. Today I will talk about assessing the security of internet paths, where we did a case study of a few Dutch critical infrastructures. I cannot move my slides. Can you help me?
Yes, you will need to say next when you want the next slide.
Oh, okay. Next. Okay. Uh, is that okay if I share my screen? It sounds a bit disturbing. Then. Okay, first I want to start with a news article published in March 2024. That was published in NOS, which is a mainstream news organization in Dutch critical in the Netherlands. It basically shows. Excuse me, can I share my computer because I have to do next multiple times?
Sorry, as I mentioned to you before, either you share the screen and you control the slides on your side, or I share them on my side, and then you have to say next when you want the next slide.
Oh, okay, next, please.
I don't see. I don't see. Have you requested to share the screen?
Oh, no. Okay, then okay.
Now you
Now I
have
have
requested to share the
requested.
screen. Okay, now you have.
Oh.
Just 1 second. Okay, there you are.
Okay, thanks. So that news basically shows that the dominance of cloud-based services, many big organizations and critical infrastructures in the Netherlands are moving to the cloud operators like big hypergiants Microsoft and Google for their daily operations. So what might be the problem? The problem is that those critical infrastructures, they should have secure paths to those cloud service providers. According to European Union Commission, critical infrastructures are those physical and information technology facilities, network services, and assets, the disruption of which impacts the health, safety, and security or economic well-being of citizens. In most of the cases, CIs needs to traverse multiple autonomous systems to reach their cloud providers. And the problem is that those CIs have limited insights about the security status of the paths. The reason is that first, they have limited visibility. They do not know how many paths exist from them to the cloud provider. And the second problem is that there exists no mechanism to measure the security of the whole path. Now, I want to start with a very high level overview of how BGP works. As you see in the figure, there exist 5 autonomous system, where autonomous system 1 is one CI, critical infrastructure, and AS5 is a cloud provider. They are connected via BGP sessions. Let us imagine a situation where cloud provider is announcing a block of IP addresses 5.5.0/24. Then it sends a BGP message to its neighbor AS4. It basically gives the reachability information to reach that prefix. Then after receiving this announcement, then it forwards it to its other neighbors, depending its AS number. So in this way, a CI will have 2 paths to reach to that cloud providers. And remember that data path is just opposite of the message path. So in this way, we have path 1 and path 2 for CI to reach to this cloud provider. And there exists a situation where AS4 might not announce its that prefix to its AS2, which is known as selective announcement. And one of our earlier presenter, Sabas, also talked about this selective announcement thing. In this way, CI will see only one path, which is path 1, to reach its cloud provider. Now let's talk about prefix hijacking and route origin validation things. imagine a situation where a service is hosted with IP 5.5.1, and in this way, AS4 will have a routing table with only one entry to reach that server. So whenever a CI does request for this IP, then it will propagate to 3, 4, and in this way it will reach to cloud provider. Consider a situation where another AS 100 comes, 000 comes, and it starts announcing more specific prefix, which is of length 25. Then in this case, AS4 will have another entry to reach to that server. And according to the standard routing model, which is Gower expert model, the more specific prefix path is preferred over less specific path. In this way, AS4 might forward its traffic to that AS1000. And this phenomenon is known as prefix hijacking, and it's a common incident in the current internet. So the way to prevent this prefix hijacking is route origin validation. And this route origin validation is a filter that basically checks the list of the prefixes and AS is authorized to announce. So in this case, if AS4 had implemented ROV filtering, then it would discard the route towards that hijacker. Now let's come to the real scenario where we have our critical infrastructures, which could be an electric grid operator or transportation system or water supply or any financial institution. In this case, we took this AS number, which is basically an ASN of a financial institution. And you can see many autonomous systems which have two types of relationship, either customer to provider or peer to peer provider. And here you can see green boxes and green ellipses and red ellipses, and green one shows that this autonomous systems implements ROV, and red one shows that it doesn't implement ROV. And whenever a CI request for its mail service provider, which is 52.101.73.21, then it has two paths. One path is shown by blue line and another path is path 2. Now consider the same situation as before, where an AS100 comes and it starts to announce a more specific prefix. Then in this case, there is a high chance that the traffic will be forwarded to this hijacker. The reason is that whenever 6453 has to forward the traffic, then it will prefer 4755 because it's a customer, and customer routes are preferred over peer route, and the peer is 3257. So as you see in the figure, this path to hole is vulnerable due to a single S4755, and this is known as collateral damage. So for a CI, it is very important to have all ASs secure in order to have a secure path. So in this work, we basically outlined two research questions. So first one is finding the number of fully and partially ROB protected paths from a CI to its cloud provider. And the second one is identifying the effect of a CI's upstream provider implementing ROB on the number of ROB protected paths. To answer this question, we have these 4 steps. The first one is path collecting, and I will explain each steps in the next slides. So I am merging these 2 steps, path collection and stitching together. Here we used public route collectors from our rice and our route views. So what we did is that we have 2 types of paths. One is the path from critical from a CI to route collector, and another path is from Microsoft ASN, which is 8075, and towards the route collector. So in this case, we identified 2 paths, path 1 and path 2. Then we find the common node between these two paths, which is basically a peer collector. And in this case, 6453 is a common ASN between these two paths. Then we found a new path as shown in the figure. Now the next step is to sanitize those paths. Sanitize means finding valid paths out of those new stitched paths. In our definition, valid paths are those paths in which prefix of a CI can reach its destination as and vice versa. For this, we checked Gauss export's model of route export and value-free conditions. Uh, so generally, route export policy defines that the route received from an AS should be propagated to which of its BGP peers. So if any of those conditions are violated, then it is called valid. So in our case, valid paths are those paths which are value free. For example, this one was the new path that we formed from our method. Then we checked their relationship between the autonomous systems using Kaida S-Rank API. And we see that these relationships does not violate value-free conditions, and which means that a prefix from a CI ASN can reach to a Microsoft ASN and vice versa. Hence, it is a valid path. Now, the next step is how to score the security of the whole path. So for this, we use ROB as a metric for security scoring. The reason that we choose ROB is basically it is the only one ready to deploy solution to prevent prefix hijacking in the internet. For scoring ROB, we use an API from Robista. That Robista does daily data plane measurement to check that which ASNs are filtering RPKI invalid prefixes. So using that Robista API, first we identify ROB scores of all autonomous systems on a path. As shown in the figure, there are 4 paths. So when we look into the first path, the first one is is a source CI, and the last one is the destination CI. So there exist 3 autonomous systems in that path, and we find that all these 3 ASs have scores of 100. So the path of the whole ROB scores becomes 100. Whenever whenever an score whenever an AS has the lowest score, then we consider the ROB score of the path as the lowest score, because as we already saw from an example, an AS having the lowest ROB score has a high impact on the security of the path. And there exist many cases where we couldn't find ROB scores of ASs because Robista currently covers around 30,000 autonomous systems. So in that case, we identified ROB score of the whole path as NA, not available. Then we used our method to do a case study for 4 critical infrastructures in the Netherlands. We chose 2 banks, one water supply company, and one energy supply company. And all these 4 CIs use Microsoft Mail for their daily operations, and Microsoft is at least 2 hops away from them. So when you look into the figure of this bank, one of those banks, the x-axis shows the number of AS hops between a source and a destination AS, uh, which excludes source and destination, and the y-axis shows the number of paths. As shown in the figure, you can see that there exist many 0% ROB paths, which means any one of those autonomous systems on the path have ROB score 0. So, and this graph shows that there exists a large number of unsecure paths from this bank towards the Microsoft Mail, and any of these paths could be chosen by the operators depending on their business policy. Now, looking at this figure of an energy supplier company, we can see that there does not exist any secure paths which is 100% ROV paths, and we see that it's all autonomous system on its paths are 100% ROV except its immediate provider. It means if its immediate provider does ROV filtering, then all of its valid paths becomes fully secured ROV paths. Then we did another analysis to find that how many unique ASs exist on those 100% secure paths. So for example, if you look into this bank one, there exist 85 paths with different hops length having 100% ROB, which means secured paths, and there exist 15 unique ASs in those paths. So it gives us insight that if these 15 ASs form a group to forward CI's traffic, and they could offer such concepts as a value-added service to their customers along with visualization. So here are the key takeaways of our work. We developed a method to calculate the security status of a path in combination with pathfinding. The second one is we found that implementing ROB fully by upstream providers will increase the number of fully ROB protected paths. So our future work considers investigating the effects on pathfinding using additionally geographically diverse route collectors. Thank you for your time and concentration. I'm hoping for your questions and any suggestions.
Thank you very
Thank you.
much, Shyam. We have a question from Tobias.
Hey, Tobias Siebig, Max Planck Institute for Informatics, and I was wondering whether you conducted any data plane measurements to validate that the paths you synthesized from the route collector information were actually feasible or taken paths.
That's a good question. Yeah, actually, we couldn't do data plane measurement because first thing is that we need to have some probes. We looked for Atlas probes if some those CIs have probes to do data plane measurement. We couldn't find, then we couldn't verify that thing.
And I see a question from Juan Camilo.
Camilo from NTT. First of all, this is very good work. You did what you could, understanding that you had no access to ISP data, right? And so you were resourceful and you gathered those paths on your own. The thing that I'm missing, and that might be very hard to get, is you did mention a specific service for Microsoft, an IP. That was the resource that it was hard that you should protect. Have you thought about considering how you could recommend, and this is hard, recommend the companies to find those type of services? Have you looked at work that finds that? Because if you cannot find the fragile services, then the rest of the work will be useless. So have you thought about that? How to automatize that work?
Oh, you mean like finding the IP address of those critical services?
It might be
like that?
IP addresses, it might be DNS names.
Okay, yeah, that's a good point. Actually, in our case, first we tried to find the IP addresses of the mail servers that are being used by CIs. Then we found the covering prefix that Microsoft announces for their mail server IP addresses. But yeah, answering your question, so we haven't thought about any method to detect those things. Maybe DNS things can help.
Very well. Thank you very much. Let's thank the speaker. Elias, can you come to the microphone? So you can see it, so you're aware of the time duration. Okay. Yeah. Cool. Room is yours.
Okay. Yes, hello, welcome to Protocol Fixes for Keytrap Vulnerabilities. My name is Elias Heftrich, and I'm one of the authors of this, and I work for Athene Research Center for Applied Cybersecurity, and I'm here with my colleague, Niklas Vogel, who's at the audience. So my talk will be structured as follows. First, we'll have a short recap on the keytrap attacks, followed by explanation on exploration of the problems with the short-term mitigations. So don't get me wrong, the short-term mitigations are good and well, they have their purpose, but they're not suitable as long-term fixes for the vulnerabilities. And so the point followed thereafter is suggestion of protocol fixes for long-term fixes for this vulnerability. And we would like to spark a discussion with you, either here in the questions time, which will be limited, I suppose, but obviously also in the hallways and wherever you want to have it. Yeah. So what are keytrap attacks, or what were they? So keytrap is, have a look. Okay, these slides. So keytrap is DOS by DNSSEC validation. And there are several attack vectors to this, and in its most potent form, it had a pretty high impact. So we managed to stall resolvers for up to 16 hours with just a single response. And it also required ridiculously little resources. So essentially all an attacker had to do was host a malicious domain and serve a malicious zone file, attract a resolver to resolve the name and that name, and yeah, I think things would get downhill. Also, all the tested DNSSEC implementations were found vulnerable. This encompasses resolver libraries, debugging tools, resolvers themselves, obviously. And to be specific, we couldn't find any DNSSEC implementation which was not vulnerable. Which also makes it sound to assume that there were quite an abundance of vulnerable networks worldwide, and also made patching keytrap a pretty critical thing. So that required tight coordination with a multi-vendor task force. Doesn't work. Keytrap exploited DNSSEC protocol design. We call that the eager validation approach, which is meant to ensure robustness against validation errors, which is first try all possible DNS keys for a signature record until one works, and second, try all possible signatures from a record set until one works. One is a must requirement in the RSCs, the other should requirement, but I'll iterate on that later. And yes, by the combination of these two requirements, for example, the specification essentially implied complex algorithms over expensive public key cryptography, and thereby allowed CPU resource exhaustion attacks on DNSSEC validators. Vulnerable requirements in the specification are actually pretty old, dating back to the 90s, and we found first vulnerable implementations in 2000 and 2004 by code review. So the actual fundamental problem which was exposed by keytrap ranges beyond eager validation. So essentially, a CPU resource exhaustion has never properly been addressed in DNSSEC. There were points here and there which pointed into some directions, some addressments of some issues, but the whole overall problem was never been properly addressed until keytrap. More specifically, the openness of DNS and the purposes of DNSSEC. Openness of the protocol semantics allow for just a plethora of attack vectors, which are keytrap-like. For instance, exploitation of DS hashing, not only signature validation, and also exploitation of valid signatures, which were covering different record sets conforming to protocol semantics and different attack vectors. So the short-term fixes, which were engineered by the task force, addressed these attack vectors, but they also introduced so far unmatched complexity, which has issues on its own, and yeah, I'll come to that now. So the first class of mitigations is architectural containment, foremost intermitting long-running validations to allow other tasks in the pipeline to proceed. And this works in preventing denial of service, but this also still allows a waste of CPU cycles. Albeit low priority CPU cycles, but we still should not allow an attacker to just ramp up CPU for nothing. So there's an issue with that. The second class, and arguably a more interesting class for us, is limiting cryptographic operations. The limits encompass a number of signatures tried to validate a given record set, number of DNS keys tried with a given signature, failed or attempted validations per message, and most interestingly of all, the signatures and DS validations which are attempted or conducted per resolution, meaning especially per client request. These per client request resolution limits extend the requirements which were made for DNS resolvers back in the RC 1035 specification already to the DNSSEC setting. But there are some problems with these per resolution limits. First and foremost, they were essentially the vendors opted for implementing their own limits, and the values themselves are either hard-coded or can be set by configuration file. So these limits are local to deployment, which is somewhat desirable. You can imagine an open resolver has different requirements and different vulnerabilities than some resolver operated in a local network. But it's also problematic, at least in the absence of a mechanism to signal and know these limits, because for one, it introduces a factor of unreliability on the domain side. Domain operator cannot really know, okay, I've configured my domain correctly, but there may be resolvers out there which have tight limits, so some validation can fail because the limits have been exceeded, and on the domain side of things, you cannot really see it. So this disincentivizes domain-side use of DNSSEC to some extent, and domain-side use of DNSSEC has issues on its own. It's been rolled out pretty slowly, so this is something we don't want to have. Second, having these limits chosen and not having some way of communicating them also means that you cannot really adapt protocol development to that, but I'll come to that later. Also, limiting DNSSEC implies limiting DNS, which is essentially a layer violation, which on its own is maybe bad design, but it adds complexity to the already complex DNSSEC, and by that hampers future DNS protocol development. So managing validation complexity in the face of especially these per resolution limited validation budgets is challenging. I brought to you some factors driving the complexity of validation, and therefore also the complexity of managing this validation limits and budgets, which is first the number of record sets requiring validation in responses. For instance, if we're going to introduce a new record type for delegation, which a delegate work group is working on, this would essentially double the complexity of delegations, double the number of signatures required for a delegation response to be validated, which is the openness of future DNS use cases being restricted here. Then there's also some elective validation cases, for instance, infrastructure revalidation. There was a presentation in DNSHub recently, if you heard that. And yeah, obviously these key tag collisions, which allowed exploitation of multiple DNS keys covering or being associated with a single signature. These key tag collisions induce natural validation failures when they arise. So not necessarily they make validation a matter of probability, but when they arise, let's imagine you have a DNS key collision in one zone with two keys which are colliding, then the worst case validation complexity essentially doubles. Secondly, these key tags don't necessarily follow a random uniform distribution. We've seen also in previous work. We've seen also in previous work that for instance, RSA, which is pictured here, does not cover the complete key tag space, and but that's just the matter of probability that a collision occurs needs to be at least considered in DNSSEC algorithm design, signature algorithm design. But yeah, the key tag calculation idiosyncrasies are configured that it's not necessarily predictable how frequently these key tag collisions are. Then there's crypto agility to be considered. Specifically, future algorithms might increase CPU load required from validation or implied by validation. And this may require a reconsideration of global limits, but these limits are set locally at the deployments as per now. So this is an issue on its own. And also different crypto libraries vary in security requirements just by switching out a library. That could mean that configuration at a resolver, which is meant to protect, is maybe not able to protect any longer. There are additional factors which promote this complexity. We enumerated some in our paper, and I think I'll just refer to that for the interested reader. Okay, what do we suggest to make things better? So first, we suggest to introduce management of these validation budgets, but essentially, if you limit per resolution the validation attempts that a resolver will perform, you already introduced something like a validation budget. So managing that by specification would be one approach to these things. So we recommend to set a global minimum per resolution validation budget in the specification, which reflects current operational insights and may be updated over time. Additionally to that, we recommend to introduce EDNS options to signal the current validation budget and the total validation budget from resolvers to name servers to make this apparent at the authoritative side. And also this would support global monitoring of these validation budgets, which would then better facilitate protocol development. Also, validation budget depletion error code can be implemented via EDNS extended errors, which would signal such an error from resolvers to clients. Our next recommendation would be outlawing key tag collisions. So just demanding key tags to uniquely identify DNS key in the zone would be blunt confrontation to current semantics, which require the opposite. And also just changing the current semantics of the current records would require worldwide coordination, which is pretty hard to enforce without breaking things. So our solution to this is to introduce a new record type, which will be a successor to DNS key, and we call that ID key. ID key features a 16-bit key ID, which is necessarily unique per zone. So it's selected by the zone administrator in distributed settings, multi-signer, for instance. The key tag space can just be segmented for one provider and for the other provider. And on the resolver side of things, we require validators to insist on uniqueness. DS records need to be replaced by analog IDDS records. This is required essentially for secure fallback to insecure mode during transition. And we don't recommend introducing new signature records, but the signature records can be repurposed by just selecting the key ID to the key tag field in the signature records. During a transition phase, domains would provide both DNS key and ID keys and set the key ID and the ID key to conform to the key tag of the DNS key record. Obviously, in that case, they need to make sure that the DNS key tags are unique as well. And IDDS and DS records can be provisioned required alongside. Resolvers supporting ID key would query for both DNS key and ID key, and either may be used for validation. And by that measure, also the adoption can be easily monitored at domains and inner transit nodes. Response sizes are kept pretty small. Only response sizes of delegation can double by this, which is also only during transition. So also note that during transition, actually, this could be streamlined with deleg when that's specified. So not necessarily, this would not really collide with introduction of delegs, or it can be streamlined to keep validation complexity of delegation small. Last but not least, we recommend to relax the absolute specification requirements, specifically to degrade the must requirements from to RFCs shown here to should. And also we suggest to warn about taking the should requirements literally, because as we've seen by Keytrap, also should requirements could be exploited for this attack. Okay, that was it so far from our side. We brought you few questions to be considered. We're also happy to answer your questions, or if that takes longer, maybe to take it to the hallway or mailing list. Thank you for your attention.
Thank you very much, Elias. We have some questions in the queue. Well, we're getting many questions in the queue. Mark, you're first.
Mark Andrews, IC. ID key is not needed for this. It literally is not needed. We have already used key IDs, key algorithm IDs to define semantics that are assigned to it. So the early keys did not know about NSEC3. All the current keys now know about NSEC3, and it's a future ongoing thing. At this point, we could just say the next key ID that to be defined has the new properties, and the validators can depend upon it. So there's no need for a type code role here. And at worst, there's a couple of duplications of DNS algorithms so that operators can move to DNS algorithms which have the new semantics. Does that make sense?
Yes, actually, I think I saw this discussion on the DNS mailing list.
Yeah,
and
I was hoping you'd seen it.
Yeah, there's pros and cons to both approaches actually, because when you introduce new algorithms, so from my side, I think that has not been posted to the mailing list yet. It also makes specification. So essentially, it would require also a specification update, because right now specification.
Oh yeah, you got a specification update either way. So
yeah, right.
So the thing is that all the existing validators can very cheaply be moved to support the new algorithms because they're just an alias. Their existing code would support the new semantics. Whether they'd enforce it or not is another matter, but they would validate against it. They may fail if the signers generate the wrong stuff, but they will definitely come back with a secure answer if they're doing the right stuff. Does that make sense?
Yeah, apart from the part, because my point is that they will certainly just, on the implementation side of things, if you just introduce new algorithms, it's not done by just introducing the algorithm, right? You're changing the semantics of the key text. So there's certainly more than just introducing.
Oh yeah, there's definitely more than introducing it, but for those which aren't particularly worried about key trap, they can just do it as an alias. And for those that are worried about it, they can do the checks in the validator anyway. So
I'm very sorry to be that horrible person that cuts a good conversation, but there is quite a few people in the queue and very few minutes left. So if you can all make questions that are self-contained with self-contained answers, that would be awesome.
Thank you.
Wes Hardiker, USC, ISI, and technically the ICANN board. They would like to remind me that I'm not speaking for them. Excellent work. Thank you, I think. One thing that I would suggest is you have very detailed recommendations based on this particular problem space. I'd love to see a higher level statement of when you are in an issue of any protocol that has multiple keys signing stuff or multiple keys to select from, what is a recommendation? You know, like if you have two conflicting keys that might be doing stuff, just stop. You know, we should only be designing protocols with one key. And then you can actually take that backwards and figure out how do you want to modify DNSSEC with the should or the must in order to build a more generic platform for how to design protocols in the first place rather than just this specific issue.
Thank you. Very interesting approach.
Hi, Robert Kishtakir, IPNCC. You mentioned a potential signaling of the global validation budget from resolver to authoritative. I guess the answer depends on how you actually want to do that, but doesn't it also help the attacker?
I suppose in some way, yes, but I think we're getting into the realm of security by obscurity if we want to prevent that, knowing the validation budgets at the attacker side, right? Because
Well,
in the
we
end-
are in that situation. Now you're giving more information to the bad guys as well.
Okay. Yeah, I think it could be a downside of the approach, legitimately, but could be worth anyways. So thank you for the remark.
Okay, thanks.
Jim Reid, just a random punter that's wandered in off the street, speaking only for myself. This is very interesting work, and I think you've given us a lot of things to think about here. But my concern is that you're trying to solve the problem, in my view, for the wrong approach. I think adding more complexity and making more tweaks to the DNSSEC protocol is probably not the best way to try and address this particular issue. From my point of view, I think the simplest solution would be have some kind of implementation guidelines or configuration hooks in the validating resolvers to say that if you do too many attempts to validate and various things go wrong, for various definitions of going wrong, just give up and return a hard fail. If we try to go further down this path, I think things get much more complicated very, very quickly, and it'll be very, very difficult to recover from that. And I think the old idea you suggested there about doing signaling to say this is the extent of my capabilities, either from the resolver to the authoritative server or vice versa, that introduced new forms of attack as well. So it's maybe best to try and steer away from that. I do think there's something worthwhile looking further into here, but I think something much simpler is needed rather than try to make changes to what is already a very brittle and very complicated protocol. Thanks.
Thank you.
Hi, this is Peter Thomason. Let me look at my notes actually. So I think you said that limits add complexity, and it's true. And it's also challenging to perhaps sometimes do validation of like a long-winded resolution within the limits. And that name servers would have to adjust their responses perhaps so that stuff fits in the limits. So I was wondering if there's any actual evidence that some things broke because limits were tightened up. I mean, they have been tightened up, and I think the consensus is that the key trap vulnerability has been mostly addressed and things don't break anymore in that sense. And so my thinking is if we really need ID key, for example, that would only be justifiable if the limits are not sufficient and really cause problems. So is there evidence for that? And a related question is that you said the limits cause complexity, but adding a signaling mechanism, of course, would be even more complexity. And it would be something that would support communicating the limits. So it would actually be pro limits, which you just said are not cool. And so, yeah, I'd like to look at the complexity trade-off between limits and signaling. So, hold on, it's just two questions actually. The complexity trade-off between limits and signaling, and whether having limits actually cause problems for the authoritative service.
Okay, thank you for your questions. So first, regarding the limits and complexity. So we essentially have introduced limits. So the question is just how much do we want to manage them? And our point is that these limits can cause bad things in the long run with protocol development, especially if these limits are chosen locally at deployment site and you're going to develop stuff and then there's, I don't know, long CNAME chains, deep referrals, and then you could just break stuff by introducing new mechanisms, for instance, select, which could double the delegation chain. So it could be worthwhile adding this signaling bit of complexity, which is, at least from my sense, not too complex, like an investment to actually manage this validation complexity or the implications on complexity from these validation budgets or limitations in the first place. It was a second question. First question was evidence of two-tier limits. Actually, at the moment, no. But again, this is a matter of long-term robustness of the protocol and protocol development process. So at the moment, there's just one thing which we identified as maybe two-tier limits, which is maybe they patched it in the meantime, I don't know. But bind9 approach was to just tolerate a single cryptographic validation failure. And in case of a delegation which requires more than one signature validation because there's NSEC3 involved or whatever, DNS key collision could actually cause, in the worst case, such a thing to fire. I mean, collisions are not frequent, that's clear, but they can happen and they do happen. And in that case, things can break. I hope that answered your questions.
Thank you very much. Let's thank Elias for a great presentation. And if the authors of the next paper, Unisub, are present, please manifest yourself. Yes. Okay, Levin, you were worrying me. I could not reach you, so the slides are there. Have you passed the control?
Sure, thank you. Okay, I can control the slides. Good afternoon, everyone. I'm Li Bin Liu from Zhongguancun Lab. Today, I will represent our co-authors to present our work, Unisub, a unified framework for internet-scale social address validation. First, let's review the necessity for social address validation. A social address spoofing leads to various malicious attacks, as described in the FC 6959, and the representative attacks are the reflective DDoS. Therefore, network operators deploy social address validation devices in the networks to block the traffic with spoofing social IP addresses. Also, since 2014, the Manos initiatively has been calling on the net operators to implement the SAL as close to the source as possible. Various SAL mechanisms are proposed and become standards in IETF. The best current practice for SAL, such as BCP38, was first proposed in 2000s, and the IFC 3704 and the IFC 8704 was proposed in 2004 and 2020 respectively. The source address validation architecture, IFC 5210, was published in 2008. Besides, IETF Survey Working Group was formed in 2008 and aimed to standardize access network source SAL mechanism that prevent nodes attached to the same IP link from spoofing each other's IP addresses. And the IETF Subnet Working Group was formed in 2022 and aimed to guide the development of new intra and interdomain SAL mechanisms, including the distributed protocols for SAL, such as DSAL, which was proposed in the IETF 113 meeting. However, recent SAL measurement studies show that the adoption of SAL is very low on the internet. This indicates that it remains a significant challenge to promote the wide deployment of SAL. We summarize three fundamental reasons for this based on the survey. The first reason is lack of understanding for SAL. Many network operators lack the technical knowledge, understanding, and practical experience. They do not know how SAL works or how to deploy or operate a specific SAL mechanism, which prevents they deploy SAL mechanisms in their network. The second one is lack of open source implementation. There is very limited open source effort on SAL. As a result, it is difficult to form an acknowledged baseline standard, leading to differences in understanding and the implementation of the same SAL mechanism. The third one is the performance concerns. Network operators cannot test and evaluate the performance of different SAL mechanisms due to the lack of a publicly available testbed. Without sufficient tests, network operators hesitate to deploy SAL mechanisms in their network. So to solve the problems, Unisub provides an open platform to implement and emulate different SAL mechanisms. Before introducing the Unisub, let's first summarize existing SAL mechanisms in terms of SAL information sources and SAL rule format, in order to motivate the design of a unified SAL framework. The SAL information sources consist of manual configurations, third-party public database, such as RPKI, ROA, and ASPA objects, and IR data, and the communication messages between AS. SAL rule format includes two types, prefix and its legitimate incoming interface, and prefix and its cryptographic key. In the table, we can see URTF, survey, and DSAL rely on the communication messages between AS and generate SAL rules with prefix and legitimate incoming interfaces. Passport, EPIC, and PASCRS also rely on the communication information between AS and generate SAL rules with prefix and cryptographic key. BASAL relies on the third-party public database and the communication information between AS and generates SAL rules with prefix and legitimate incoming interface. Ingress filtering relies on the manual configurations and generates SAL rules with prefix and the legitimate incoming interfaces. In sum, this work first revisits existing SAL mechanisms from a high-level perspective and summarize a unified architecture that can cover all existing SAL mechanisms and possible future ones. Besides, existing SAL mechanisms consist of their basic functions for collecting SAL information, generating SAL rules, and executing SAL filtering. And they are different in SAL information source or SAL rule format. Therefore, we propose Unisal. Here, the figure shows the architecture of Unisal. The SAL agent is a core of Unisal, which has three primary modules, including the SAL information collector, SAL rule generator, and SAL enforcer, and two data structures, such as the SAL information base and the SAL table. The SAL information collector collects the SAL information from one or more SAL information sources and consolidates the collected information into the SAL information base, abbreviated as SIB. The SAL information base is a data structure that stores the SAL information consolidated by the SAL information collector. And the SAL rule generator processes the SAL information stored in the SIB and output a SAL table according to the SAL algorithms. The SAL table is a data structure that stores SAL rules generated by the SAL rule generator. And the SAL enforcer performs SAL on the data plane by using the SAL table and the SAL executors, such as ACL, P4, and IP tables. We have implemented 9 SAL mechanisms, including 8 existing SAL mechanisms and 1 new SAL mechanism. The 8 existing SAL mechanisms include URTF-based SAL mechanisms, such as loose URTF, strict URTF, FP URTF, EFP URTF with algorithm A, and the EFP URTF with algorithm B, BASAL, passport, and DSAL. The new SAL mechanism is called enhanced DSAL, abbreviated as EDSAL. EDSAL makes the 3 improvements upon the DSAL. First, it reduces the size of the communicated information by using the S number to replace source prefix of the corresponding S within the communicated message. Second, it implements a neighbor discovery mechanism for building neighbor relationships. And the third, it decouples the control and the data plane channels. Only the control channel reuses the BGP connection of the underlying router. EDSAL uses the control channel to exchange information to establish and maintain neighbor relationships, as well as to set up data channels with neighbors. For exchanging essence, EDSAL uses a data channel. As shown in the right figure, along the proportion of SAL messages increase, the control plane performance of EDSAL decreases slower than DSAL. In order to evaluate the performance of the SAL mechanisms on top of Unisal, we create the SAL benchmark. build the real world AS level network topology according to these following steps. We collect the real BGP data from public route collectors provided by route views and the route race. Pass and extract AS path attribute from the BGP data and obtaining the neighboring relation between AS. We create links for the neighboring AS to build the AS level internet topology and obtain the business relationship between AS according to the data from CADA. Then we generate subgraphs based on the fault topology, which are the connected components of the fault topology. Also, we assign the routing policy based on the business relationships and the value-free principle. We also adopt 3 classic scenarios, including symmetric routing, no export, and the direct server routine. For the evaluation setups, we use x86 server machine with 2 26-core CPUs, 256 gigabytes RAM, and 2 1 terabyte SSDs, and 1 12 terabyte HDDs. On the server machine, we run Ubuntu with kernel version 5.15 and use Docker for each container to emulate an AS. We run Bird as the AS board router and use IP tables to filter the packets on the data plane. Based on the testbed, we evaluate the performance of the cell mechanisms in terms of cell accuracy, control plane and data plane performance, and scalability. And except for the scalability demands, we use a network topology with 50 AS in our evaluation. And we vary the deployment ratios of the cell mechanisms from 10% to 100% to emulate different scenarios of partial deployment. Here, the table shows the cell accuracy of different cell mechanisms implemented on top of Unicell in the scenarios, including symmetric routing, no export, and the direct server routine. We can see the table shows that the cell accuracy results of different cell mechanisms. In symmetric routing scenario, both loose URPF and the EFP URPF with algorithm B may improperly permit spoofing traffic. Then in no export and the DSR scenario, both loose URPF and the EFP URPF with algorithm B may improperly permit spoofing traffic. Strict URPF, LP URPF, EFP URPF with algorithm A and algorithm B, and BASAL may improperly block legitimate traffic. Also, these environment results are the same as the theoretical analysis in the interdomain subnet problem statement draft. Okay, here the figure shows the control plane performance for processing pure BGP messages in terms of packets per second with varying proportions of cell messages over the total number of messages for cell and the pure BGP. We can observe that both DCell and the EDCell impact the efficiency of the control plane in dealing with pure BGP messages. But the underlying reasons are different. For EDCell, its limitations arise from the resource constraints within each container in our emulation. Instead, DCell not only need to communicate more cell messages, but also necessitates additional resources for passing the delivered cell messages. Then let's look at the data plane performance. The figure shows the data plane forwarding performance of the cell mechanisms with varying deployment ratios. Here, we employ IP tables to execute the cell on the data plane, and we implement a traffic generation tool to generate packets with fixed 1.5 kilobytes to evaluate the data plane forwarding performance in terms of packets per second. Here, passport always has a more significant impact on data plane on data plane forwarding performance as we can observe than the other sound mechanisms. And the data plane forwarding performance of each sound mechanism decreases as the deployment ratio increases. This is because the size of the sound table within each ES increases with the increase of deployment ratio. A larger sound table results in longer query time for each incoming packet. And let's look at the scalability of Unisound. The figure shows the experiment completion time of Unisound across different network skills. In this experiment, we vary the network skills by increasing the number of AS for the testbed experiments, and then calculated the whole completion time of the experiment. And the experiment completion time is the longest time elapsed from launching the Docker environment, launching the emulation environment to generating complete sound table on the data plane among all AS. In the experiment, we vary the AS numbers from 25 to 200. Also, we take D cell and ED cell as the sound mechanism as the sound mechanisms. Both experiment completion times for D cell and the ED cell increase along with the increase of S numbers as we observed in the figure. And compared to D cell, ED cell shows a slower growth trends with the increase of network size. We analyze that this is because ED cell converges faster than the D cell. Okay, here is a summary of the drafts which related to our work in IETF. Thank you very much. I'm happy to take your questions.
Thank you very much, Levin. Are there questions? While people think about questions, can you talk a little bit about how would you see the deployment of Unisub? How would you do the deployment? And you were showing the scalability of it. What incentives would people have to actually deploy Unisub?
I think Unisub is an open platform, is an open software platform. People can use it to emulate their networking environments and deploy different sound mechanisms to test the performance of sound mechanisms in their target network environment. And then, based on the results, they can determine the appropriate sound mechanism for them. And also, they can, for the researchers, they can also develop new sound mechanism based on Unisound and compare the performance with other existing sound mechanism to show their performance improvement or other design improvements. Yeah.
Yeah, thank you very much, Levin. If there are no other questions, let's thank the speaker.
Thank you very much.
And see everybody after the break. Short break, I'm afraid. Is it? Okay. Six presentations, 15 minutes each. Okay, yeah, then there is definitely something wrong with it. Am I correct? You are probably correct. I will check it. Sorry, I really need to run to the toilet. Okay. I'm afraid. But don't worry.